Today's talk, we're going to talk about topic 5.1, electric fields. Alright, so here's the overview for 5.1. Understand the concept and properties of electrical charge, apply Coulomb's law, understand the concept of electric fields, with electrical current and direct current, and understand the concept of electric potential difference. So what is charge? Electric charge is a property of matter that causes subatomic particles to experience a force when placed in an electric or magnetic field. So charge can either be positive or negative. Protons are positive charges, electrons are negative charges, and we measure the charge in the unit of coulombs. Now, once again, a lot of this should not be new to you. A lot of this is stuff that you probably covered in middle school science, for example. Alright, so let's talk about some properties of charges. So, electrical charge is a quantized value. This means that the amount of electrical charge on the body is always an integral multiple of a basic unit. And so, for example, the basic unit of a charge on the proton is equal to 1.6 times 10 to the minus 19 coulombs. We denote this value as E. And of course, electron would be negative E. Even though the proton and electron have different masses, the charges are the same value, but an electron is just negative E. And E stands for the elementary charge. So, what is electrical force? Right, electrical force is a force that attracts or repels charges. Once again, not new. Like charges repel each other, so two protons, two electrons will repel each other. Opposite charges attract each other, so a proton and an electron. Alright, so Coulomb's law. The electrical force is also called the Coulomb force. And so we can calculate the Coulomb force by taking Coulomb's constant times the magnitude of charge 1 and charge 2 divided by the distance between the charges squared. And K is equal to 1 over 4 pi epsilon naught. And K has a value of 8.99 times 10 to the 9 coulombs. Newton meters squared coulombs to the minus 2. Alright, so what is permittivity? Well, it is a measure of the obstruction due to an electric field. If something has relatively high permittivity, then the electric field forces will be weaker. Alright, this constant epsilon is called the permittivity. We measure permittivity relative to the permittivity of free space or a vacuum, and we denote that as epsilon naught. And so it has a relative permittivity of 1. Here, for all intents and purposes in most calculations, you can assume it's the same as a vacuum. Paper has a high one in 80, right? And so there are some problems in IB physics that do deal with relative permittivity. So the relative permittivity is the ratio of the permittivity of the material divided by epsilon naught. Alright, and so it tells you, for example, if you have 7.1 over 8.85, you would get 80. That's relative permittivity. We 80 epsilon naught. Alright, and so for example, Coulomb's law with relative permittivity, you would have 1 over 4 pi epsilon naught times epsilon sub r and Q1, Q2 over r squared. So epsilon naught is, for example, epsilon r is, for example, 4, then you would have 4 times epsilon naught. Alright, so let's take a look at some example here to calculate the Coulomb force. Two charges with a charge of 6.0 microcoulombs and negative 3 microcoulombs are separated by a distance of 3 centimeters. What is the electric force between the two charges? Step 1, you put in the charges, and here we get electrical force is negative 179.75 newtons. Now, the negative and positive is not the direction of the force. It tells you if the force is attractive or repulsive. And so if it's positive, then we have a repulsive force. For example, a positive times a positive, two protons will give you positive, or a negative times a negative will give you a positive. So the magnitude of the force, positive and negative, tells you if it's attractive or repulsive. It does not tell you the direction of the force. Do not get that confused. So here we have an electron and a proton, therefore it's going to be a attractive force, so therefore it's going to be negative. So how do we find the force on more than one charge? For example, I have a force to the right here from Q1, and I have a force to the pulling it also to the right from Q3. So how do we find it? Well, that's the superposition principle, that the force on any charge due to the number of charges equal to the vector sum of all the forces on that charge, taking one at a time. So we take the force of this one, Q1 onto Q2, and then we take the force of Q3 on Q2, and then we can find the charge. We add them together. Once again, you determine if it's positive or negative depending on the direction. So here we have Q1 is pushing Q2 to the right because it's a repulsive force. So that's going to be a positive magnitude. And then here we have Q3 pulling Q2 to the right. And that's also going to be positive. So the vector sum is going to be a positive number plus a positive number. Once again, when you're doing Coulomb forces, the positive negative only tells you if it's attractive or repulsive. But when you're taking the vector sum, you got to think about the direction that it's being pulled or pushed towards. Alright, and so once again, here we go, the vector sum of that. So once again, we got the force of Q1 on Q2 and Q3 on Q2, and therefore we add them together, and that's how I get the total force. Alright, electric field is an interesting concept. Electric field is the force per unit charge. Since electrical charges experience a force at a distance, i.e. a field force, it has to make sense that there exists some type of field that causes the charge to experience this force. And this is electric field. So for example, with gravity, there's the gravitational field, right? There's a gravitational field that attracts objects with masses. For electricity, there's electric field, right? Field forces, there has to be some kind of field that exists, and that's going to be the force per unit charge, and that's what we call the electric field. Alright, so electric field lines represent the strength of electric field exerted by a charge, a larger charge, which will have more field lines. So if I have a 1 Coulomb charge and a 2 Coulomb charge, well, the 2 Coulomb charge should have twice as many field lines. And we draw field lines coming outwards from a proton inwards to an electron, and neutrons have no field lines because they had no charge. So again, protons, it goes outward, and electrons, it goes inward. So, for example, question here, what is the force experienced by a 4.5 microcoulomb point charge and electric field with a strength of 380 newtons per coulomb? That's going to be equal to, well, E equals F over Q. Well, then that means F is simply E times Q. So we take the force times the charge, and we get a force of 1.71 times 10 to the minus 3 newtons. Alright, let's talk about electrical current. Okay, electrical current is the flow of electrical charges. The unit for current is the ampere. Simply, it is a measure of how much charge passes through a point in a given time. So I means the change in total charge over change in time. So there's two types of current that we deal with, and one is called direct current. It occurs when the current always flows in the same direction. And then it's alternating current. It occurs when the current changes its direction back and forth, hence the name alternating. Right, and alternating can happen many times per second, current going back and forth. And there was a big push, if you want to look into the current wars between Thomas Edison and Nikola Tesla, versus AC versus DC. There's benefits to both, and you'll see why we use AC for transferring current and DC for everyday devices. But in this unit, IB only focuses on direct current. So we're not going to digress into alternating current at the moment. So how do we measure current? Well, I know this seems simple, but the IB physics loves to ask this question, this concept. Current is measured using an ammeter, which is connected in series with the circuit. And we'll talk about what it means to be in series later on in this course. Alright, and so another thing that's really odd in physics is that we always draw a current in a circuit, often using conventional current. Alright, and so often we assume the positive charge is moving. Now, is that correct? Absolutely not. But when Benjamin Franklin was coming up with this idea of charge, in the metal. He wasn't sure whether it was the positive charge that moved or the negative charge that moved. So he guessed and he said, well, I'm going to guess it's positive. And so if you draw the positive charge, you go from the positive end, right, to negative end, because the positive end of the cathode is going to basically push the proton towards the negative end. However, we learned that was not the case. In fact, in real life in metals, the negative, the negative charge of it moves, so it actually goes from negative end to the positive end. And that's what we call the electron current. And you could draw an electron current if you wanted to, if you made a distinction, but just for convention, we always draw the conventional current, which we draw from going from the positive end to the negative end, even though we know deep down that it's the negative current, the negative particle that moves. But, old habits die hard, I guess. Alright, the main point of IB physics here, at least 5.1 with current, is going to be the drift speed, or drift current. Alright, and so electrons move at random velocities in wires, so they're bouncing around just how molecules in the air, they're colliding with the walls of the material and having those ionic interactions. They're bouncing off each other. It's not smooth sailing from point A to point B, unfortunately. Alright, think about it as a bunch of drunk drivers driving through bumper cars. That's basically how electrons move through a wire. And so the drift speed is a measure of the average velocity of the electrons as it moves through a wire. So you see some electrons going faster, some going slower. Alright, and so just like on a highway, you have some people who are in the right lane going 10 under the speed limit, then you have people in the left lane going 40 miles over the speed limit. And so the drift speed of a highway would be the average speed of all the drivers on the highway. So in a wire, it's the average speed of the electrons. Alright, and so that's going to be I equals to N times A times velocity times Q, where N is going to be the charge density of the material, A is the cross-section area of the wire, V is the velocity of electron, and Q is the drift speed, and Q is the charge of the electron, which we said was negative 1.6 times 10 to the minus 19 coulombs. Alright, once again, how did we get here? Well, I is delta Q over delta T. Well, that means then V times delta T times A, right? That's going to be times the charge density times the charge of the particle. This would be negative E for electrons, delta T, and so I equals N times A times V times Q. Alrighty. And so then, last but not least, big part of 5.1 is energy transfer in electric fields. So we call the work energy theorem that work is equal to the change in kinetic energy, which equals, of course, the negative change in potential energy. Likewise, if you recall from topic 2, when you drop something from height, right, it goes from potential to kinetic energy. Well, the change in kinetic is a negative change in potential. This is just a conservation of energy. The work energy theorem is just a conservation of energy. And this is a theorem that comes into play all the time in IB physics. So it's definitely a theorem that you should recognize and know and love and maybe live by for the rest of your life. At least until you pass the IB exam, whatever floats your boat, I guess. Alright, and so, which would be buoyancy. In order to move a charged electric field, a force must be applied. For example, moving a small positive touch charge towards another positive charge requires a force to overcome the repulsive Coulomb force between the two charges. And for example, if it was a positive charge towards a negative charge, well then the electric field would be doing work versus you doing work in an electric field. Alright, and the work required to move a charge between 2 points is called the potential difference, and this is what we call the volt. The unit for this is the volt. And voltage is work per unit charge. The electric field is force per unit charge. Voltage is the work per unit charge. And for example, a 1.5 battery provides 1.5 volts of energy to each electron. So voltage is work per unit charge. So here's an example. The work done in moving a 2.0 microcoulomb between 2 points in electric field is 1.5 times 10 to the minus 4 joules. Determine the potential difference between the 2 points. Well, I know that voltage is work divided by the charge, and here we have the charge of 2.0 microcoulombs, and therefore the voltage is going to be 1.5 times 10 to the minus 4th divided by 2.0 times 10 to the minus 6th. Hence, we get a voltage of 75 volts. And a big concept they love to test that in IB Physics 2 is the electron volt. The joule is too large a unit of energy for the small world that electrons are in. Alright, the whole other world down there, and things behave very differently, and that's how we came to the foundation of quantum mechanics and modern physics. We realized that, oh, things on small scales don't really behave the same way they do on the scale that we're used to in everyday life. And so Newtonian mechanics, which now we call classical physics, started to fail, and so that's how we came with the whole idea of quantum mechanics, but I digress. Alright, and so the main point here is that the electron volt is defined as the amount of work done when a charge of negative 1.6 times 10 to the minus 19 coulomb is moved through a potential difference of 1 volt. So basically, electron volt is taking an electron and moving it through a potential difference of 1 volt. Alright, and so electron volt is 1 eV is 1.6 times 10 to the minus 19 coulombs times 1 V. Don't forget, work is Q times V. And so, therefore, electron volt is going to be Q, the charge of electron, 1.6 times 10 to the minus 19 coulombs times 1 volt, the potential difference. Alright, and so 1 volt is 1 eV. That means that if we have an electron through a 50 volt, it's going to be 50 eV. And that means that if we have, for example, a 2E charge, well, going through 100 volts is going to give us 200 eV of energy. This is why the electron volt is so convenient. In the IB exam, they love to test this concept. Sometimes they ask you, what is the meaning of electron volt? What does it represent? You can say, well, it's what taking the work done to take an electron through 1 volt potential. It might ask you how much it is in joules. Well, that'll be 1.6 times 10 to the minus 19 joules. And so, electron volt is something you should definitely know, because on every IB paper I've seen, there's some question that asks about whether in calculations or as a concept, what is the electron volt? So electron volt is definitely a concept that you should definitely know. Alright, and once again, converting electron volts to joules, you take work is equal to Q times V, and so 500 eV times the charge of the electron, or whatever the charge it is in coulombs, you come back to joules, so 8.0 times 10 to the minus 17 joules. So once again, if it was 1 volt, or 1 eV, that's 1.6 times 10 to the minus 19 joules. And so if it's 500 eV, well, that's 8.01 times 10 to the minus 17 joules. And I guarantee you, in some capacity, whether it's in paper 1 or paper 2, there's going to be some type of question that's going to require you to go from eV to joules. So make sure you know this process too. Alright, and that's it for topic 5.1. We'll dive in here to 5.1, some example problems, and then into some 5.2 as well.